In this video, we are going to talk about Cisco's implementation of the rapid spanning tree. Similarly to the traditional spanning tree, which Cisco implements on per VLAN basis, rapid spanning tree on Cisco switches, on Catalyst switches, is implemented on per VLAN basis, and it's called Rapid Per VLAN Spanning Tree Plus. Since I am going to be focusing mostly on changes and improvements in comparison to 802.1d and PVST implementation of spanning tree on Cisco switches, I highly recommend that prior to watching this video, you get very familiar with the traditional spanning tree. The first thing that the rapid spanning tree does somewhat differently in comparison to the per VLAN spanning tree, the traditional 802.1d, is the format of the BPDUs. There are still two types of the BPDUs. We have the configuration BPDU and we have the topology change notification BPDU. But the configuration BPDU is a little bit different. First of all, the version field in the BPDU claims to be version 2 instead of version 1 in 802.1d. Also, you may recall that in the BPDU header, we do have some flags. And the most important flags that we had in the traditional spanning tree were the topology change and the topology change acknowledgement. But here, with the rapid spanning tree, we do have additional flags. Things like the proposal, agreement, the port role, forwarding, or learning flags. And these flags are going to be used in a process called the synchronization that I'm going to explain a little bit later on. Also, another fundamental difference between the traditional spanning tree and the rapid spanning tree when it comes to the BPDUs is how they are propagated. You may recall that in the traditional spanning tree, the BPDUs are generated by the root switch and then flooded by the other switches. In other words, other switches will not generate BPDUs on their own unless they actually hear from root. And if they stop hearing from the root for the duration of the max age timer, they're going to run a new election, and the switch that becomes the new root is going to start generating its own BPDUs. In rapid spanning tree, every switch upon hearing from the root is going to generate its own BPDUs that are going to look identically to those BPDUs sent by the root, but they're going to be sent independently from the root. That means that if we stop hearing from the root, we are still going to be sending these BPDUs out. The reason why this is done is to be able to detect the failures in the network faster. Let me show you these things in action. So the first thing we are going to do is we're going to take a look at the format of the BPDUs, and to do that I'm going to set up a very simple network consisting of two switches, Cat1 and Cat2. Cat1 will be my root switch here, and it's currently configured to run the traditional spanning tree. This is port Fast Ethernet 24, and to port Fast Ethernet 03, I have a Wireshark station configured. So what I want to do here is I want to take a copy of any frames sent on port Fast Ethernet 24 and send them to Wireshark. I'm then going to capture these frames, the spanning tree frames, and I'm going to take a look at the header format there. After I capture one or two spanning tree BPDUs, I'm going to change the spanning tree here to run in rapid mode. So let's first confirm the configuration on Cat1. So if I do show spanning tree here, I can see that I'm running IEEE protocol, which is Cisco's way of telling me that it runs in the traditional per VLAN spanning tree mode. I also see here port Fast Ethernet 24, which is a designated port, and it's in forwarding status. So let's go to our Wireshark here, and I'm going to start the capture. And at first, I'm not going to get much here because this is going to be capturing traffic from the interface facing my Wireshark station, and this is not what I want. So I'm first going to limit the display to only spanning tree, and then I'm going to go back to Cat1 and I'm going to configure my span session. So I'm going to say monitor session 1 source interface Fastnet 24. I'm interested only in the transmitted frames, and I'm going to say monitor session 1 destination interface Fastnet 03 encapsulation replicate. So now when I go back to my Wireshark, I can see here that I'm receiving some spanning tree BPDUs. And what I'm looking for here is the protocol version identifier, and it says 0 here, which tells me that this is a traditional spanning tree. So I'm going to restart this capture. I'm going to start capturing again, and on cat1 I'm going to change the configuration to operate in a rapid mode here, and I'm going to stop the capture now. We can see here that the protocol has changed. We can see here that this is a configuration BPDU, and here it says it's RST. The RST stands for the rapid spanning tree. Now we can see here that the protocol version identifier, here it says rapid spanning tree. It says 2 instead of 0 that we had before. Remember, type 1 is going to be the topology change notification BPDU. And here I can see these these multiple flags. I can see the topology change acknowledgement, I can see the agreement, the forwarding learning, the port role proposal, and the actual topology change flag here. Also, the other field here is the timers. They are very, very similar to what we had in the traditional spanning tree. So this is how the frame format looks like. This is how the BPDU looks on the wire for the rapid spanning tree. Going back to my slideshow here, I can see that topology change notifications are also going to be sent in the rapid spanning tree environment, but these are going to be frames that are going to be sent only for the backwards compatibility. The rapid spanning tree is designed to actually coexist with the traditional spanning tree. If we are receiving the correct spanning tree frames, if we are receiving the rapid spanning tree frames, we are going to be operating in the rapid mode. If we are not receiving the rapid spanning tree BPDUs, if we are receiving the traditional spanning tree, the spanning tree will operate in the traditional 822.1d mode, or on Cisco in the PVST mode. Similarly to the traditional per VLAN spanning tree, the rapid per VLAN spanning tree relies on different timers for its operation. Of course, the most important timer here being the BPDU hello time, which is the interval between BPDU transmissions. By default, it's also set to 2 seconds. We also have the forward delay, which is the time the port will spend in the transient states, and we will see what the transient states are in rapid spanning tree. They are somewhat different than in the traditional spanning tree. By default, the forward delay is 15 seconds. There is also the maximum age, the max age timer, which is mostly used for the backwards compatibility with the traditional spanning tree. It is also, by default, 20 seconds. All of these timers can be modified, of course, either directly in a case of the forward delay in the max age, and indirectly using the diameter-based calculation for max age and forward delay. And of course, the hello time can only be modified directly. I have explained in great detail the calculation based on the diameter in the video that discussed the per VLAN spanning tree. I mentioned that the port states in the rapid spanning tree have been somewhat changed, and here they are. First, we have the disabled state. This is not standardized state, but it's the state when the port is really shut down or turned off. We should give it some name. I personally like to call it the disabled state, but remember, this is not part of the spanning tree definition. This is why I put it in the parentheses. Then we have the discarding phase, or the discarding state. Discarding state is very similar to the blocking state in the traditional spanning tree, in a way that no data is being sent or received in this state, and that the BPDUs are received and accepted, but no MAC addresses are learned, and also BPDUs are not being transmitted in this state, similarly to the blocking state in the traditional spanning tree. The next phase, or the next state, is the learning state, and you may have noticed that there is no listening state in the rapid spanning tree. The reason for that is that the mere existence of the listening state is a little bit obscure. It is designed to prevent unnecessary flooding of the traffic in our network. It really doesn't add much to the stability of the network or to the convergence times or loop prevention, which is the primary and really the only function of the spanning tree. So in rapid spanning tree, we are skipping away the listening phase and we are moving directly into the learning phase. And here, no data, no production traffic is going to be sent or received on this port. The BPDUs are going to be transmitted and received. The MAC addresses as well are going to be learned. And this is, as the slide here says, the combined listening and learning state from the traditional spanning tree. And the forwarding state, of course, is the forwarding state. The production traffic, the data traffic is being transmitted, is being received. In a case, the other side is actually sending us something, but that's the whole point, isn't it? And the BPDUs are also going to be sent and received on the port. The MAC addresses, of course, are being learned. The rapid spanning tree convergence is not unlike the convergence in the traditional spanning tree. The very first thing that happens in the network is the root election, and this process is identical to the root election in 802.1d. The election is always on. We have the permanent state of democracy, as I like to say. Every switch in the network is eligible to become the root. The only thing that it has to do to become the root is to claim to be the root, and this is based on the bridge ID, which consists of the bridge priority and the bridge MAC address. The bridge priority, of course, is the number. The lowest number wins. The default value in Cisco switches, in Catalyst switches, is 32,768. But here, when we are running the spanning tree or the rapid spanning tree in per VLAN setting, we have to remember that we have the extended system ID, which is going to be the VLAN number. So, for example, for VLAN 1, the default bridge priority will be 32,769 because we are going to add one. We are going to add 1 to the priority, which is our VLAN number. Similarly, if we had VLAN 10, we would have to add 10 to our priority. The bridge MAC address is the lowest MAC address on the system, sometimes referred to as the system MAC address. On most of the Catalyst switches, it is going to be the MAC address which is by 1 lower than the lowest port ID on the switch. In the case of fixed configuration switches, this is easy to determine, and in the case of modular switches, it would be usually the MAC address which is by 1 lower of the lowest port number on the supervisor, on the active supervisor in the switch. And finally, after the root has been elected, each switch needs to calculate the actual spanning tree topology. It needs to determine whether the ports are going to be the root ports, the blocking ports, the whatever the port roles actually are there. And in rapid spanning tree, the port roles have also been changed similarly to the port states, and I'm going to talk about that in just a minute. So the port role determination is based on two things. First, are we on this port receiving version 2 BPDUs? If we are not receiving version 2 BPDUs and we are receiving version 0 BPDUs, that means the traditional spanning tree, what's going to happen is that the port is going to operate in the traditional way, in 802.1d way. So all the rules there are going to be followed. This port cannot operate in rapid mode. That means it cannot benefit from one less port state and some other things that I'm going to explain in a minute. But if we are receiving version 2 BPDUs, that means we are operating in a rapid mode, what's going to happen with this port, how is it going to transition into its final port role, is based on something that is called the port type. The rapid spanning tree recognizes different port types. Port types play a crucial role in rapid spanning tree convergence process. First, we have to understand how are ports separated, how are they divided into different categories from rapid spanning tree's perspective. The first division is to edge and non-edge ports. Now, what are edge ports? Edge ports are ports that are configured with a feature that is very, very similar, if not identical, to spanning tree port fast feature from the traditional spanning tree, or the Cisco's enhancement to the traditional spanning tree. In Cisco IOS on Catalyst switches, the edge port functionality is configured identically to the old port fast. That means you don't have to remember any new syntax. The only difference is that this behavior is now standardized. Now, for non-edge ports that are also not going to be root ports, why am I making this emphasis on non-root ports is going to become clear when we go to the next slide here. But for these ports, the non-edge, non-root ports, we have two possible options. One is that they are considered by the spanning tree to be point-to-point ports, and the other one is that they are considered to be shared ports. Now, what is the difference between these two? First, the assumption behind the point-to-point port is that it is connected to a single device. That means it cannot be a hub behind which we have multiple devices. We are expecting only a single device to be on this network segment. For shared ports, this assumption is not true. We cannot guarantee that there is going to be only a single device behind this port, so we are going to behave differently. How differently is going to become clear, as I say, in just a minute. This separation to point-to-point or shared ports is determined by default based on the duplex setting on the port. If the port is operating in full duplex, we are going to assume that this is a point-to-point port. If the port is operating in half duplex, we are going to assume that this is a shared port. This, of course, can be forced, changed, configured, and the command for that is on an interface spanning tree link type, and then we can specify either point-to-point or shared. But let's take a look at why is this important for the rapid spanning tree convergence. During the convergence, edge ports and non-edge ports behave differently. Also, the non-edge port that will become the root will behave differently than other non-edge ports. So let's take a look at this. The edge ports are going to transition to the forwarding state immediately. Remember, the edge ports are the ports that behave in identical way to port-fast ports. The port-fast is a conditional state on the incoming BPDU. The same thing for edge ports. If there is an incoming BPDU on the port, this port will not be edge port and therefore will need to converge in the same way as other non-edge ports. The non-edge ports behave differently whether they are point-to-point or shared ports. The point-to-point non-root ports are going to attempt to use a process called the synchronization. I will talk about this in great detail. This is the major difference in comparison to the traditional spanning tree, and this is what makes rapid spanning tree actually rapid. It's this process of synchronization. If the synchronization fails, the port will need to go through the normal convergence process. That means that it will have to transition from discarding state to learning state and finally to forwarding state. And this is timer dependent. In discarding state and learning state, it will need to spend a certain period of time. In learning state, it will have to spend at least forward delay period. The shared ports, again, non-root shared ports, cannot benefit from the synchronization. Why? Because shared ports, by definition, may be connected to more than one device. And if that's so, we cannot very quickly negotiate with the other device using the synchronization process, which is designed to work only on point-to-point non-edge ports, and we have to go through the normal convergence. The port that will become the root port on the switch will simply transition to forwarding state immediately. It will not go through the normal convergence process of going through the discarding and learning phases of rapid spanning tree. It's not only the convergence process that has changed in the rapid spanning tree. The port roles have changed a little bit as well. First of all, the two roles that are identical in the traditional spanning tree and the rapid spanning tree are the root port and the designated port. The root port is simply the port that receives the BPDU with the lowest root path cost. It's the port on the switch that is closest to the root. The only switch in the whole network that will not have any root ports will be the root itself. All other switches will have one and one root port only. The designated port is the port that transmits the BPDU with the lowest root path cost on the segment. Think of it as designated port will be the upstream port to the root port. These two roles exist in traditional spanning tree as well, and they are identical. However, in the rapid spanning tree, we have two additional roles. One is the alternate port, which is simply the port that is transmitting the BPDU that is superior to our own BPDU, but it is inferior to the BPDU received on the root port. These ports are going to be in a blocking state, but we know that we can actually reach our root through them. In a case of the root port failure, one of the alternate ports can be immediately transitioned to become the root port, and remember what happens with the port that is a root port, it can transition to forwarding state immediately. The backup port is the port that is connected to the same network segment as one of our other ports. But this port has lower either port priority or the port ID, whatever makes it less desirable to become the designated port on the network segment. Now, I should maybe explain the alternate port and the backup port in a little bit more detail. So I'm going to head to my whiteboard and I'm going to show you the example of the alternate ports and the backup ports. I am again going to use a very simple network to illustrate these features. Let's have two switches, Cat1 and Cat2. Cat1 will be the root in our network, and both of these switches are going to be running rapid per VLAN spanning tree. I'm going to have two connections between Cat1 and Cat2. This connection here will be on port Fast Ethernet 23 on both sides, and this will be on Fast Ethernet 024 on both sides. Now, given that Cat1 is the root and everything else is the default, these two ports on Cat1 will be designated ports, and they're going to be forwarding. On Fast Ethernet 23, I'm going to be receiving a BPDU that is going to be superior than the one on Fast Ethernet 24. Why? Is it the same root ID? Yes. Is it the same sender bridge ID? Yes. What about the port priority? It will be the same by default, 128. But what about the port ID itself? The port ID will be lower on Fast Ethernet 23 than on Fast 24. That means that Fast Ethernet 23 will win. That means that this port here becomes the root port, and it will automatically transition to forwarding. But this port here will be discarding, so let's just write this here. Let's be clear what I mean by this. And this port here will actually be an alternate port. Why would it be an alternate port? Because this port does receive a BPDU that leads back to root without going back through Cat2 itself. Let's take a look at this in the terminal. So I have this configuration already set up. So if I take a look at the output of show spanning tree on Cat1, I see that I'm running per VLAN rapid spanning tree, and this is how it's going to be identified in iOS. And here I have two ports, and I can see that they are both designated ports and that they are actually forwarding right now. On Cat2, if I do show spanning tree, I will see that Fast Ethernet 23 is indeed a root port and is forwarding, and Fast Ethernet 24 is an alternate port, and it says here it's blocking. But we know that this is not true state, that the true state is actually called discarding. So this was the alternate port. But what is the backup port? Imagine that we had a setup that looked like this. We had a switch, let's call it Cat1 in our case, which is the root, which is connected to the same shared segment here, where we may or may not have other devices. But it's connected to the shared segment with two ports. Let's say that this is port 23 and that this port here is 24. Now, what's going to happen here is that both of these ports are going to be transmitting BPDUs, but they are also going to be receiving each other's BPDUs. But in this case, what's going to be the same is the root ID, the sender ID, the priority, but the port IDs are going to be different. The port numbers are going to be different. 23 is going to be better port than 24, but in a case that 23 fails, is 24 a path back to the root? Well, no, it isn't, because cat1 is the root itself. So fast24 here should be in discarding state. It should be blocking, but it's not a backup path. It's not an alternate path to the root. It is instead going to be a backup port, because it is a backup for the designated port. So the way you can think of alternate, it is alternate for the root port, and the backup is actually a backup for the designated port on the same shared segment. Now, the shared segment usually involves some hubs. Unfortunately, I don't have any hubs in my network. So how can I simulate this setup so that I can show you the backup port in action, so that I can show you on the switch the backup port? Well, what I'm going to do here is very simple thing. Again, I'm going to have my cat1 connected to cat2. I'm going to have ports 23 and 24 on both sides. But what I'm going to do here on cat2, I'm going to turn off the spanning tree. What that is going to cause is the BPDU sent from fast Ethernet 23 will simply be forwarded out fast Ethernet 24 back to cat1 and vice versa, which means that I should see port 23 being the designated port in forwarding state, and fast Ethernet 24 will be a designated port. Sorry, it will not be the designated port, it will be the backup port in the discarding state, or as Cisco is going to tell me, the blocking state. So going to my terminal, show spanning tree now shows me this situation here, and on cat2 I'm simply going to say no spanning tree VLAN 1, and if I do show spanning tree on cat1, I can immediately see that fast Ethernet 24 has become a backup port and is blocking. This means that if fast Ethernet 23 fails, so let's fail fast Ethernet 23, let's shut it down from the other side. If I shut down fast Ethernet 23, what I can see here is that the backup port is now in a blocking state. When the backup port needs to transition to become a designated port, it will need to go through the timers. It cannot converge immediately. So now what I'm going to see here is it's going to spend the forward delay in the blocking state, in the discarding state. It's going to go into the learning state. It's going to spend there 15 seconds by default, and only then it's going to go and start forwarding. But the important thing is here, I scrolled all the way up. This was a backup port, and when I shut down fast Ethernet 24, we can see that at one point it changed the role to the designated port. So this is when the timer, when the forward delay timer started counting down. Now, we can see that for the designated port, when it goes through the process of moving from the backup to the designated port, we have to go through the timers. So we have to go from the discarding state, we have to go into the learning state, and then we go into forwarding state. But when alternate needs to transition to become a root port, it's simply going to go from discarding state into the forwarding state. Does this sound familiar to you? If it does, you would be absolutely right, because this is almost identical to Cisco's uplink fast feature. However, there is one significant difference. You remember that the uplink fast, when this transition happens automatically, it's going to spoof some traffic, it's going to start sending the frames sourced from all the MAC addresses it has in its own CAM table. In a case of alternate port transitioning to the root port, this does not happen. So it's a very similar feature to uplink fast, but it's not identical to it.